this unit, we're going to learn about angular resolved photoemission spectroscopy, Arpes, that had played a fundamental role in the understanding of topological states of matter because of its direct imaging of the electronic states in these materials. Here you can already see two imaging of canonical topological states obtained with Arpes, where on the right we see a topological insulator, and on the left we see a topological whale semi-metal. What we see on the right is the bulk, conduction, and valence bands, and in between the characteristic Dirac surface states that signify the topological insulator in bismuth selenide. In tantalum arsenide on the left, we have a slightly more complex image where we have both trivial and topological surface states, the Fermi arcs, that reside on the surface. In both these images, we see momentum space versus energy imaging of the band structure of the material. In order to understand the way Arpes actually functions, we need to go about a century back to the days of Einstein that put forward the concept of the photoelectric effect, for which he also got the Nobel Prize, where we shine a radiation, photons, on the surface of a material, and they rip out electrons with a quantized amount of energy, which is the photoelectric effect. And this was indeed proven to be so by the experiment of Millikan. Photoemission spectroscopy in general, and Arpes in particular, use this mechanism in order to study the spectroscopy of electronic materials. In order to understand better the interaction between electrons and photons, we have, of course, to consider the Hamiltonian that has both the electronic terms and the terms coming from the radiation photonic field. This is the part of the electrons where we have the gauge invariant kinetic energy term that has the vector potential in particular that, as we'll see, has the photon radiation field in it, and possible other coupling perturbation terms, and of course the radiation field, where we occupy the photons one by one with their respective dispersion. This is the form of the vector potential that has the radiation field in it with their plane wave representation. What we will do next is separate this Hamiltonian to electron and photon only processes and to the interaction term that couples them one to another that will take perturbatively. So here is our unperturbed Hamiltonian that has the now non-gauge invariant kinetic energy, has the radiation field, and to it we add the interaction term and we expand it in orders of the vector potential. So the first order in the vector potential has single photon processes, the second order has two photon processes, and so on. And in this unit, we will only consider single photon processes. What we do next, of course, is we can diagonalize the unperturbed Hamiltonian and find the eigenfunctions and eigenenergies both of the electrons and of the radiation field, and use them in order to calculate the transitions of the electrons, their excitation by the radiation field using Fermi golden rule. Here what we have for now is the initial and final states of the whole system of the electrons, disregarding the interaction between photons and electrons, which is given by the interaction term. We'll take a first approximation, which is the dipole approximation, under which, again, we retain the first order term in the vector potential, but also now when we plug in the phasor of the photons, the plane wave, what we'll do is take the long wavelength, which is the dipole approximation, which means that the wavelength of the photon is much larger than the wavelength of the electrons, and therefore we retain only the first order term of this phasor, which is just unity, which leaves us with these matrix elements that we now need to calculate. And if we assume centrally symmetric potential, we obtain the selection rules, orbital selection rules of the excitations of electrons by the photon. Up until now, we've discussed only the excitation of the electron by the photon. However, in reality, inside the sample, the electron, the photoexcited electron, has to go through several other processes in order for us to be able to measure it. First of all, it has to travel through the bulk of the sample until it arrives at the surface of the sample, and then it needs to escape through the surface potential before it can travel in vacuum towards the detector. In principle, quantum mechanically, what we have to do is to describe all these processes together as a single stationary process. So these initial and final states that we have here actually includes the excitation, the travel to the surface, the escape from the surface, and travel in vacuum, which is a very complex calculation to do. So now we will take another simplifying approximation that actually separates these three processes into three consecutive processes that feed one another. The first is the photoexcitation of the electron in the bulk. The second is the travel of the photoexcited electron through the bulk up to the surface, which is governed by the mean free path of the electron inside the material. And lastly, the escape of the photoexcited electron through the surface of the material. So the radiation field that we have available places us within 1 to, let's say, kilo eV of radiation energy, which translates into a universal curve for the typical mean free path that we can draw more or less on a single curve that you see here, which means that in reality, the mean free path of electrons inside solids is extremely short and ranges between, let's say, 5 angstrom up to at most 100 angstrom within this energy range. This means that Arpes is indeed a very surface sensitive probe. Only when we go to lower energies or higher energies, we can probe slightly deeper into the bulk, and indeed photon energy is used in order to probe more bulk states than surface ones, but in general, Arpes is restricted to the surface of the material. So now we are ready to understand how Arpes actually works in the lab. We have a radiation source. We shine the surface of the sample, which excites electrons that emit in all directions. We collect a certain solid angle to which the electrons are emitted and collimate the beam into the detector. What we have first is this double hemisphere structure, which are biased one with respect to another in order to deflect the motion of the electrons towards the detector, which is positioned on the other end of the hemispherical structure. Because the electrons enter with different energies, this deflection takes them to different points on the surface of the detector, and therefore along this axis we actually have the spectrum, the dispersion of the emitted electrons. Now along the other direction, we already have a solid angle opening from which we will next extract the momentum of the electrons. However, we want to scan here all momenta, and to do so, we'll have to scan all solid angles emitted from the sample. In order to do that, we can do two things. One is rotating the sample. The other is rotating the detector with respect to the sample. Now we have the three ingredients that we need in order to calculate the momentum of the traveled electron in the vacuum, although at the end we'll want to extract the momentum and energy of the electrons inside the sample, not as they travel in free space, but let's start from there. So we have the energy and the solid angle, and we can simply calculate the three momentum components of the momentum vector, px, py, and pz. Two of them, the in-plane momenta, are simply related to the momentum the electron had inside the sample. This is because in the in-plane direction, momentum is conserved. We did not break translational invariance. Therefore, px and py that we calculated from the kinetic energy and the solid angle that we recorded are simply related to the momentum, in-plane momentum, the electron had inside the sample. So now we're missing only the third component of the momentum vector, the out-of-plane direction, where translational invariance is actually broken. When we photoexcite the electrons and the photon transfers its energy to the electron in the bulk, after it elastically travels to the surface, it needs first to overcome the work function, which is localized on the surface of the material. So some of that kinetic energy is invested in overcoming the work function, and therefore, when we plug in the kinetic energy into the formula for calculating the out-of-plane momentum, we must account for this work function, which is generally unknown. So one thing that can be done is now to tune the photon energy, extract the work function, plug it into the kinetic energy term, and from it find the out-of-plane momentum of the electron as it had inside the sample. By doing this, we can map the spectrum that we measure outside the sample to the spectrum the electron had inside the material. So now we have the full dispersion of the electrons as they had it inside the material, energy, and the three directions of momentum. Luckily, in topological states of matter, we're many times interested in the surface states, and therefore, learning from Arpes only the in-plane momentum versus energy dispersion of the electrons is the essential part in order to resolve, for example, the Dirac surface states on the surface of topological insulators and the Weyl surface states on the surface of Weyl semimetals.